Good morning, students. We're going to be having our lesson on patterns in algebra, lesson 21 on page 88 and 89. This is all about interpreting line graphs, or linear graphs, sorry. Um, we have been working towards this. We are familiar with ordered pairs, and I have an example written down right here, 7, 4. An ordered pair is written with the first number always representing x and the second number always representing y. You can also write this down as input and output. Input is the number that we put into the equation. Output is the result of putting that number in the equation. Okay, so we're trying to make sense of how to recognize and understand linear graphs and making essentially gathering information from them because it's a very useful way to provide information. Um, I like the question that you guys ask me every time, Mr. Koch, why is this? How is this relevant to us? So, when would we find linear graphs? I think that's a good question to ask. And if you look in the newspaper and you follow weather patterns and stuff like that, that would be something of a linear graph. Typically, you see a lot of evidence represented on graphs. You can also use linear graphs to understand maybe how much time has passed since something occurred, or there's a lot of different ways and reasons that we would use linear graphs. Tracking even your fitness levels. That's a really good one. Or heartbeat. What your heart rate is while you do exercises. These are all things that you use linear graphs for, and you may not use them now at this time when you're in grade 7, but you should be using them in the future. And you've probably interacted with linear graphs in some sense. If you've done any sort of research, then you've probably interacted with linear graphs at some point. So it's an important skill to use and to understand. And the most fundamental part of linear graphs is understanding, well, first, how do you read the information? And we need to understand how to use an ordered pair. Okay, so that is, we use the first number is always the x value and the second number is always a y value. So if we look at right here, I made this graph. I just called it graph A, and I should actually have it. I'm going to call this input, and I'm going to call this side output. Okay, so now I have I have my title and I have my two labels for my axes. And I can say, okay, so 1 comma 50 is one of the ordered pairs on this linear graph. Because I line up my 1 and I go to the 50 point, because I'm counting by tens, I just didn't show them all. My next one would be my input of 2 and my output is going to be 40. Input of 3, output is 30. Input of 4, output is 50. Input of 5, output is 10. So here I wrote this down as a t-table. So if I have a graph, I can turn that into a t-table. And if I have a t-table, I can turn that into a graph. This could also, if I wanted to, I could actually write this as a sequence. If I wanted to write this as a sequence, what it would look like is something like this. I'm going to write down here. I'm going to say 50 is my first number, and then 40, and then 30, and then 20, and then 10. That would be a sequence. Now, there's one thing that I'm not leaving in, which is my input value, but you should be able to figure that out because this is the first term. So term number 1, so I input 1, term number 2, term number 3, 4, 5. Right? So I can really represent graphs. Graphed information can be written down as t-tables or sequences, and I can reverse all these and sort of change them across, and I can do all sorts of interesting things. If we were to find a rule for this one, this is a bit of a weird one. It took a little bit for me to understand what rule I could write down, and this is the rule I came up with. Now, your rule could be slightly different than mine, but the most important thing about rules is it has to be true for every number in the set, and then it's a good rule. So this is what my rule is. I said 60 subtract input times 10 gives me an output. So what does that look like? So I have 60 as my original number, and I'm going to subtract input times 10. So in this one, my input's 1. I'm going to do input times 10, so that's just 10. So 50 subtract 10 equals, 60 subtract 10 equals 50, which is what came out as my answer. This next one I have 2. So 60 subtract 2 times 10, which is 20. So 60 subtract 20 equals 40, and I get my right answer. So if you were to test this for every single one of your numbers, which is a good practice to do, especially because we only have 5 terms, we would have a good rule here. Okay. Now this page is all about using your graph information to make sense of the world around us. You'll have examples of costs increasing or distance being traveled and those sorts of things. Your job for this class and for this rest of this unit, we're going to be finishing up this unit pretty soon, is to make sense of this graphed information and be able to start feeling comfortable with switching to t-tables, to graphs and to sequences and just rotating all through all these. Okay. For this page, page 88 and 89, I'd like you to do the questions 1 through 4, which is 1 through 3 is found exclusively on 88. Number 4 is the very first one of the sets, and then also number 7. Okay. If you can go through those sets of questions, that'd be really helpful. You can always do more than that. And if you want to check your work, you can send me a message and I can go over it with you. And we can do it that way. Okay. So I hope you have an excellent morning and I hope it's a productive day.